The Hough transform is a tool in the field of computer vision used to identify things such as straight lines and circles in images. I couldn't find any great explanations of this algorithm when teaching it, so hopefully this video will come in useful if you're studying the subject or just generally curious. Just to warn you though, it will be heavy on equations, so don't operate any heavy machinery while listening. We are dealing with computer vision, and images on a computer are composed of pixels. Pixels are simply points in space with x and y coordinates. I'll talk about this more at the end, but one way to identify objects in an image is if there is a strong contrast, such as a dark object on a bright background or a light colored line on dark asphalt. Then the edge of the object might be any dark pixel with a bright neighbor or something like that. A computer can very easily iterate over the image and pick out all such pixels, but this would merely produce a big list of x and y coordinates. The purpose of the Hough transform is to take a set of pixels of interest, identify if any pixels lie along one or more straight lines, and then get the mathematical description of those lines. I should be clear, this is not linear regression or curve fitting or anything like that. We are not committing to putting a best fit line through some points. Any 2 points will lie on a straight line, of course, but we want to identify where many points sit on or very close to a line. There may be multiple lines identified in an image or none at all. First, a note on the name. The algorithm is named after Paul Hough, who described it in a 1959 paper, and I believe the correct pronunciation for his last name is like the word rough. This paper used the algorithm to identify the tracks of subatomic particles going through a bubble chamber. Next, I want to massively overcomplicate something as simple as a straight line. You are probably familiar with a linear equation y equals mx plus c, where m is the gradient and c the intercept. In 2 dimensions, 2 parameters like this are enough to uniquely define a line. The problem with this description is that a vertical line would have effectively infinite gradient. Certainly, it would be useful to identify vertical lines in images without the computer running into errors with overflow or division by zero. There is an alternative polar coordinate representation. Instead of having a gradient as such, let us denote each line by the angle theta which it makes with the vertical. Let's have theta going anti-clockwise, taking a value from 0 to 360 degrees, so that a line at 45 degrees looks like a backslash, and at 135 degrees looks like a forward slash. For a given angle, there are infinitely many possible lines, each one parallel, but separated by some distance. The way we will uniquely distinguish between the lines is by taking r to be the shortest possible distance from the line to the origin. The distance r is then different for each line, and together the 2 parameters r and theta uniquely specify a line. For a given straight line, just how can the distance of closest approach be calculated? The easiest way to think about it is if you think of the line as a long road and a house at the origin. The shortest possible driveway which can be built will join the road at a right angle. Thus r is the length of a construction line which intercepts the original line orthogonally. This property allows us to do some trigonometry to convert from this new r and theta representation to the usual gradient and intercept. If you are studying this, here are some formulas to convert between the two on the screen and a suggestion on how to prove them. Unfortunately, this is going to get a bit more confusing, but bear with me. Let's now consider lines which go through a particular pixel, a point in space. Suppose we have some point P, which I will denote by a green circle to make it look like a P. It has coordinates xp, yp. We can choose any angle we like and draw a line with this angle theta to the vertical going through P. Now, it's easy enough to find the distance from the origin to P using Pythagoras' theorem. But the thing is that point P is not, in general, the point of closest approach of a line. To find the closest approach, you will need to move forwards or backwards along the line. In my analogy, it means that you have to travel along the road before you can turn into the driveway. But there are other possible lines inclined at different angles to the vertical, all with different distances of closest approach. Any line passing through P must satisfy the equation r equals xp cos theta plus yp sin theta. I'm showing some more hints how you might prove this with trigonometry on the screen. The location of P sets the x and y coordinates. We chose what we want theta to be as an independent variable, and then r comes out of this equation. Once more, make sure you don't confuse r as the distance of closest approach with the distance to P itself. Now that we have all that out of the way, we can finally get on with the Hough transform. We have an equation which the parameters of any possible line passing through point P must satisfy. We can plot this relation with r as a function of theta, and it is a sinusoid. This is a transformation into what is called the parameter space of r and theta. Of all their possible combinations, only those along this curve represent valid lines passing through point P. There is a subtlety here I won't go into too much. For every line with a given theta and positive r, there is also a line with theta offset by 180 degrees and negative r. It is as if the second line is in the same place and running in the opposite direction to the original. They are both identical if written as the usual y equals mx plus c. To avoid double counting every line, I will simply limit r to be positive and chop off the negative half of the parameter space. So, this is the curve for P, but let's now add a second point Q with new coordinates xq, yq. This will have its own curve in the Hough parameter space. Where the two curves intersect are the parameters of a straight line that passes through both points. There is indeed a line which connects 2 points, and this is it. A third pixel which lies on the same line in real space would transform to a curve also intersecting at the same place. Such a point where curves from multiple pixels intersect is called a knot in the original Hough paper, and these are of course what we're after when looking for edges in images. It's unlikely that real pixels would be so neatly lined up, which would lead to the knot being rather spread out. The curves in parameter space would not meet at a single point. On the other hand, the algorithm for line detection doesn't need such a precise intersection. The angle theta is discretized, the shape of the parameter space being evaluated perhaps every degree or half a degree. As an example, here is a simplified, pixelated letter A. I'm going to transform each bright pixel in turn to parameter space with a spacing in theta of 1 degree. Three knots have emerged. One with a theta at 90 degrees to the vertical, or in other words, the horizontal crossbar of the letter A, then a line at 30 and another line at 330 degrees for the two diagonals. The algorithm can pick out these knots to get the required lines from the image. The method works. A real image might have many more knots, but the approach is still the same. Straight lines aren't the only things that can be detected in this way. In principle, it's possible to transform from pixel coordinates to the parameter space of any function, a parabola for example. A knot in such a parameter space would allow different pixels to be connected by a curve in real space of the form y equals ax squared plus bx plus c. More useful for real-world problems is a Hough algorithm variant to detect circles. A circle would have three parameters: the two coordinates of its center and its radius. It makes sense for an algorithm to focus on one value of the radius at a time, which reduces this back to a problem of two parameters, xc and yc, the coordinates of the center of the circle. The question is, where could a circle which passes through point P be located? Well, if you think about it, that is itself a circle. In other words, we are looking for a valid location for point C, the center of a circle which passes through P. Then P must also be the center of a circle that passes through C. By this logic, a single point P maps to a circle in parameter space. Multiple pixels have their own circles, and any major intersections are knots which indicate where a circle should be placed. Here is an example of how this works with a pixelated emoji. The whole thing is 80 pixels across, so I'll pick a radius of 40 pixels and then transform each bright pixel in turn into parameter space. When the transform is complete, there is a knot in the center of the emoji where we can put down a circle which threads through the pixels on the outside of the emoji. Although it looks like the knot may be split into two parts because of the rough way I drew the emoji freehand, so half the pixels lie on one circle and the other half on another. We could repeat this for circles of other radii, such as the eyes. Once again, this can all be repeated algorithmically for more realistic images. To summarize, we are able to use two types of Hough transforms to identify any lines or circles present in images and obtain the precise parameters required to define them, things like the gradients of the lines. Finally, I'd like to say a few words on how such clean groups of pixels at the edges of objects can be identified. Usually, something like the Canny edge detection algorithm is used, which could be the topic for a whole separate video, but I'll attempt to summarize it here. The idea is to look for any sharp changes in the brightness of pixels. This can be done with the three colors red, green, blue, but it's usually easier to first convert to grayscale, whereby each pixel just has a single brightness value. Each pixel is checked for any sharp changes in brightness. This is done by applying a convolution, an important term in computer vision and machine learning, which you can think of as a weighted sum over adjacent pixels. For example, add together the brightness of the three pixels to the right, including two diagonals, and subtract away the pixels to the left. If the pixels on the right are brighter, then this sum would be large and positive. If the pixels on the left are brighter, it would be negative. If the brightness to the left and right is more or less equal, whether it's bright or dark, this sum turns out to be small. This quantity is then the horizontal change in brightness, a change in x. Similarly, by adding together the values below and subtracting away the ones above the pixel, a vertical change in brightness can be calculated. Together, these two can be formed into a vector. The change in x is the x component, the change in y is the y component. This vector, with its magnitude and direction, represents how the brightness is changing in the vicinity of the pixel. Back to finding the edges of objects then. Certainly, wherever the magnitude of the gradient is large, namely any pixel with a gradient larger than some threshold, this is an edge pixel. But also, any pixel with a moderate gradient adjacent to any existing edge pixel is also considered an edge. With lists of edge pixels thus identified, they can be Hough transformed as we have discussed. There are several other short steps before detecting lines and circles in practice. It's a good idea to first condition the image, such as blurring or eroding it to remove small details and noise. If you are studying this subject in practice, you are likely using or are familiar with the OpenCV software library, which has efficient implementations for everything I've discussed. There is a small GitHub repository with a couple of Python scripts and an OpenCV example in the description if you're interested to try this out yourself. On the other hand, I thought this was also a very interesting piece of applied mathematics. I've never before had to use the polar representation of a straight line, so that was a neat twist on something that schools teach from about the age of 10. Thank you for watching.